Okay, so let's get started. This class is going to be a little bit different. Well, obviously because it's online, but even from my other class, today is going to be the only day where we're going to have any slides. So most of it is going to be either on an online whiteboard, which I've set up, or we'll have it following the coding. So I think that in itself will be a bit of a challenge. I guess ideally you would have 2 monitors, but obviously not everyone's going to have access to that, so that you can both sort of code along with me while seeing what I'm doing at the same time. So I'm not exactly sure the best way to deal with that. If anyone has suggestions, I'm all yours, but definitely you can speak up and ask me to slow down at any time. I taught my undergrad class yesterday, and I think one thing that worked really well is that if you have questions, you can just type it in chat. Then you don't have to like unmute yourself and speak up, although you can if you want. In Zoom, we should walk through quickly some features in case people aren't familiar. If you kind of move your mouse around, there should be a little pop-up on the bottom that has a whole bunch of menu icons. One of them is the participants, and if you click that, it should give some options about doing things like raising your hand, which I'll try and keep my eye out for if you do want to speak up. Otherwise, as I was saying, there's another option called chat. If you open that, you should be able to just type messages. And I'll also try and keep my eye out on that. It'll be a little bit trickier here because I had a TA in my other class who was sort of prompting me when people were asking questions, but I will try and do my best. And feel free to chime in while I'm lecturing if I'm not seeing your question. Okay, so before we begin, does anyone have any questions? No? Okay. All right, intro to data analysis. And obviously, let's see, I want to quickly address kind of the elephant in the room, coronavirus, pretty crazy times right now. So class, I think, doesn't necessarily need to be your highest priority right now, and I'm totally okay with that. And so if there are any sort of circumstances causing disruption in your life thanks to this pandemic, please let me know, and we can be flexible with lots of things, and it's going to have to be taken on a case-by-case basis. In the syllabus, you'll notice that there is a participation grade, but don't worry about that. Attend the class if you can, but also it's going to be recorded, so you can view it either on the embedded Aggie video on Canvas, or I'm also going to put it on YouTube. So I would say, this can't and probably shouldn't be the highest priority in your life right now, but to the extent that you want to be have some normalcy in your life, then hopefully we can take this opportunity to sort of continue on taking classes and doing research and all of that good stuff. Okay, hang on a second. I noticed that my chat bar has disappeared. Open those back up. Okay, so what is this class about? Bridging the gap between theory and practice. So some folks will have taken some probably more rigorous theoretical classes in econometrics or regression, and maybe your econ or statistics. So you might be, pretty familiar with this kind of stuff on the left, and maybe somewhat with the stuff on the right. But I think that there is a lot of practical use of regression that maybe is a little less emphasized in some classes. And so when we're thinking about going from raw data to our sort of final project, thinking or final product, not project, going to explore the data, thinking about forming your regression output, and interpretation. We really want to focus on sort of the procedure across all of this application of data analysis and regression. So the basic schedule of the course may change, right, due to our ongoing situation, but basics are quick intro and review of programming. And so on this point, it's actually going to be a little bit different this year from years past, actually not because of coronavirus, but there has traditionally been a course in civil engineering, which was required for TTP students, taught by Deb Niemeyer. It was an introduction to R. Unfortunately, she has left, and that class has been somewhat voided. And so it has typically been not a required, but a useful precursor to this course. So what I'm going to do this year is to take a little bit more time and adding a little bit more material for the Learning R and R tutorial. So we'll spend a little bit more time there. And then we'll delve into regression analysis, look at unsupervised learning, and then case studies and project presentations. Course overview, grades, class participation, homework, final project. So again, don't worry too much about class participation. We're going to be pretty flexible here. For homeworks, there's going to be, I think well, geez, I'm mixing up my different courses. I think that there are 4 problem sets, each one worth 10%. And then for the final project, you'll be analyzing a data set of your choice and try to employ techniques learned throughout the class. And we'll talk a little bit more about the final project down the line. Obviously, the presentations will have to be online, but hopefully by then it'll be pretty easy, or everyone will be pretty familiar with the system, that it shouldn't be a problem. The final project does allow for groups, which means that you will have to communicate with your partners online. Okay, so the basics of programming is going to cover basically walkthrough in R. I know some folks have approached me and asked about doing this in Python, which is totally fine with me. The actual platform isn't going to be a problem. It's just that as we go through the R tutorial, obviously things are going to be slightly different. Yeah, and so you'll have to sort of figure out the analog of what I'm doing in R in Python. We're going to cover functions, practical things to learn and understand, and how to deal with data, including comparisons of doing processes programmatically versus doing it in Excel. We'll also think about cleaning data and learn how to do that. So I wanted to give kind of a quick overview. Okay, wait, sorry, I see a question. What is big O? So big O notation is a method of thinking about how long certain algorithms and processes take. And so it's a useful concept to keep in mind. It's something that's taught in computer science, but as you do practical things in research, you may find that like, oh, if I run things through a for loop, it might take a couple hours, but if I run it through like an apply function, it might just take a couple minutes, right? And so learning a little bit about how to identify those types of issues and how to deal with that. So we won't learn too much about the theoretical aspect of Big O, but we'll see how it's useful for practical application. Yeah, so this is a high-level sort of overview of a bunch of different languages that are commonly used in fields that conduct our type of research or are sort of peripherally close to our sorts of research. And I wanted to quickly cover some of the background behind some of these things in case folks are interested. Let's see. So a lot of the statistical analysis that we're doing obviously aren't just relegated to being done in R. There are a lot of platforms to do them. R is mainly based in the statistics community. It's exploded over the last decade, but originally it was meant to just do sort of statistics analysis. Python originated in computer science. It's a higher level programming language, but it's very sort of similar to R. It has deeper functionality, especially because you have object-oriented programming and class functions, which aren't something that's available in R. I would say that you can analogously do most operations in R in Python and sort of vice versa. But some things are going to be easier to do in R, some things are going to be easier to do in Python. Generally, we choose R for data analysis tasks and for statistical analysis because that's sort of what it's meant to do. These database programs, software are great for handling large amounts of data. You're not going to be able to do sort of the same functionality in terms of any statistical analysis, but you can actually link R and Python to things like SQL and MongoDB. And the power of SQL and DB is that they are these well-tuned databases that handle relational tables. And so if you have like a super large data set that, for example, you can't even load into memory, so say you have like 100 gigabyte data set, you wouldn't be able to open something like that in R and Python. And so with SQL and DB, you can actually store it on your hard drive and query from it with speeds that are comparable to holding it in memory. So these database programs are really powerful, really widespread. These are the back end of lots and lots of different databases and data sets, including even websites online will use these as a back end. So we're not going to really do anything with these database software because none of the data sets that we're going to be using really warrant using something this powerful, but it's something to keep in mind in case you are doing something with a large data set. Optimization software. so Ample and GAMS are both commercial software that can do optimization and optimization of sort of any form. When we talk about doing regression and data analysis, those are actually types of optimization. So when we talk about ordinary least squares, for those who are familiar with that concept already, in regression, you are minimizing the sum of the square distance between your observed and your actual point. And so anytime I say minimize or maximize, that means optimization. But for the purposes of what we're doing, we're not going to be coming up with our own algorithms to solve regressions. Those have already been sort of well developed, so we won't really need to touch these. They would be sort of overkill for the types of things that we'll be doing. Let's see. Actually, before I get there, I don't know if I have a little thing about this group here in this corner, SAS, SPSS, JMP, Stata. These are commercial software that are similar to R in functionality. They're meant for doing data analysis and statistical analysis of data, and they're all paid, and so we don't have commercial licenses for all of them. I would say a lot of these are rooted in specific specific disciplines, much like R was originally coming from statisticians. Stata, for example, is commonly used by economists. SAS and SPSS used in certain industries. Social sciences, some other social sciences really like to use SAS, I believe. Yeah. LaTech is kind of a separate type of thing. This is a word processor, so you might think about Word as a way of creating documents and whatnot. LaTech is a nice programmatic way of doing that. If it's something that you want to learn, the way I learn and the way I encourage folks to learn is to do it, is just to use it when you're sort of just taking a class. So do all of your homework in LaTech, for example. So if you want to take the opportunity to do that, this would be a good time. Okay, I see a question from Vishnu. So when do we use other solvers like SEAPLEX, Gurobi into these platforms? Okay, so the solvers that you're referring to are specifically optimization solvers, and those are routines that are implemented through other platforms usually. And so SEAPLEX is the actual thing that solves the equation for you, and it is agnostic to the platform. So I could actually load SEAPLEX into GAMS or into MATLAB or into Python and use that to solve an optimization. Gurobi, similar, although Gurobi actually has its own platform, so it's kind of both. I don't know, I'm actually not sure if R has functionality to integrate with SEAPLEX yet. I'd be kind of surprised if it didn't, although I'm not 100% sure. Yeah, and so SEAPLEX and other similar solvers are things that would be implemented within one of these platforms. But again, that's overkill for the types of things that we're doing, because a lot of the regressions that we're doing already have analytical solutions and don't need to run through numeric solvers. Okay. One sec. My mouse is frozen. Here we go. Okay, and then kind of the big elephant in the room is Excel, which actually totally swamps in terms of number of users, basically all of these other software combined. And so Excel has time and place and is useful, but for what we're doing, it would be very difficult, not impossible. But it would be very difficult to apply a lot of the stuff that we're learning, and I'll try and show in some cases where it'll be or how you would do things in Excel versus in other programming languages in a more programmatic way to demonstrate the power of being able to do certain types of operation programmatically versus manually in Excel. Let's see, a couple questions coming up. Can LaTech directly print our output? Yes. So let's see, there's some packages in R and actually in LaTeX as well, which allow for sort of integration between the two. So if I did, I think SWeave is a package in R that lets you print out like LaTeX code that can be sort of transferred over, and it lets you print out the outputs in R. I'm not so familiar with it, but I can put together a quick tutorial on that. And then another question is Parquet's another database language that can be used. So I'm actually not familiar with that. Yeah, so don't know the answer. I can look into it though. Yeah, okay, as I was mentioning, statisticians are the ones who originally used and developed R. In terms of software, which ones are free? All the ones circled in green are open source and free. And actually, one of the nice things about working with free software is that it has typically a larger user base, and I can pretty confidently say that that's true for every sort of software here, maybe with the exception of like MATLAB compared to Octave, but having a larger user base is nice because when you go to look for help online, for example, it's a lot easier to find guidance and support for the free software than it is for any of the paid ones. I guess I didn't talk about Octave. That is the open source free version of MATLAB, which a lot of you might be familiar with if you're coming from an engineering background. And Octave has a lot of this. The back end of Octave is built very similar to MATLAB, where everything is sort of needing to be structured in like matrices. It was a little more common to do machine learning in that platform maybe a decade ago. But since then, the sort of prevalence of users in R and Python has led those two platforms to be kind of the standard go-to for machine learning these days. Okay, so then besides those, we will once we get through the R tutorial, we'll talk about regression analysis, linear regression, how do you do it, pitfalls and misconceptions, including a lot of things that aren't typically covered in your typical statistics or econometrics classes. We'll talk a lot about the differences in prediction versus causality, which is kind of a big dueling ongoing debate in the fields of regression, especially when we think about the approach of econometricians versus the approach of machine learning, and how that gap has been bridging, and things to think about as you do applied data analysis. We'll talk about logistic regression, and then dive into some semi-parametric and non-parametric regression, which is more sort of on the end of predictive types of regression. Thinking about pros and cons there. Yeah, great. And so that's sort of a high level overview of what we'll be covering in this course. To give some motivation, I wanted to give some examples of regression analysis that I think are pretty interesting and have made some kind of a difference in when it comes to application of data and what people have learned. Here's a pretty old example, looking at rainfall and crop yield and being able to predict basically crop yields 1 year ahead of time, and looking at how observed values compare against the forecasts, which you can see in the solid line versus the dotted line. This is one of the earliest examples way back, I think in the 1960s, early 1960s through the 1970s, when a lot of this analysis was being discovered and applied for the first time. And you can see, well, it's pretty cool that we can use some of these techniques to do prediction and looking at crop yields with a fairly high level of accuracy. And this would be kind of entirely unimpressive these days with the types of regression that they were doing, but also keep in mind that they didn't have strong computational power back then, and so a lot of the methods for some of the simple regressions were pretty innovative and still sort of carry through to when we learn about introductions to regressions today. A lot of those techniques are applied for basic linear regression, for example. Cigarette smoking and lung cancer, looking at the number of cigarettes smoked per day. And so this, I think, was the first, coming from the first publication that tried to link smoking and cancer levels. And this comes from hospital data, and was a fairly innovative application at the time of sort of looking at real data to figure out sort of correlations and causations of medical outcomes with risk factors. Pretty neat there. A little bit more recently, looking at correlation, or not just correlation, right? Regression analysis of test scores, GPA and SAT and college admissions, and being able to look at factors that lead to success in getting into college. I think sort of coming off of a lot of this type of analysis spurred conversation about, or more sort of social conversation about other factors that led to success in college admissions, including things like race and income. A lot of that is derived originally from analyses like these, and so hopefully these last couple examples gives you guys some view of the type of impact that data analysis can have, sort of even on broader social problems and social and economic problems. Here's another one that probably hasn't had as much traction in a place like the US, but I think that there's been a lot of great statistical analysis done on the relation between gun control and gun crimes. So this one is, I think, a particularly interesting example where the analysts were able to take advantage of something called a regression discontinuity, where in Australia in 1996 or 1997, they actually enacted gun control laws. And so you could observe things that were happening before and after, and then you can make some kind of conclusions about the effect of implementing it on a whole variety of different types of gun crimes, right? So homicide rates, suicide rates, unintentional death rates, and so there's been analogous sorts of research on gun control globally, but actually not so much in the US, and there are actually some political reasons for that. The NIH, which is a really big funder for health and epidemiological research in the United States, is actually not allowed to fund any research into gun-related health outcomes. And so there hasn't been nearly as much sort of data analysis on gun control effects in the United States compared to a lot of other countries, unfortunately. Probably one that a lot of you folks are hopefully interested in is thinking about CO2 and global temperature. We don't, I'm fairly certain in this course we don't have like any climate change skeptics or anything like that, but in terms of actually thinking about what the effect is and understanding the relation between CO2 and temperature, it's on both the left and the right hand side, which are measuring different types of global temperatures. We can actually use the data to measure what that effect is, right? And so these are fairly simple applications of linear data analyses that is already pretty easy to see an effect, measurable effect, and a fairly accurate one as well. You can include other variables to try and control for some of that noise variation around that line, which we'll cover when we think about multivariate. But even with just a simple one variable x mapping to a y, you can see the trend and understand basically the relation between concentration of CO2 and temperature rise. And lastly, I pulled up this example from a paper that was obviously very recently published. You can use regression to do things like predicting coronavirus spread. And so here, looking at a number of factors in a logistic regression to look at how the coronavirus epidemic is spreading in two different countries, and they have a whole bunch of different sorts of controls to be able to look at the actual factors that are influencing propagation of the virus. So on each of the graphs, you have a predicted line, which is the black, and then the dots are indicating the actual measurements. And you can see how well they've done with the prediction. Yeah, so I'm gonna pause here. Actually, you know what? We'll go to the next slide and have folks start to do this. So I'm gonna use some of this for the upcoming tutorial. So if you all wouldn't mind hopping onto this website and just sort of filling it out. It actually doesn't even need to be accurate information if you don't want, but it'll be putting together like our quick first sort of class data set that we can use. And in the meantime, as we're doing this, please let me know if you have any questions or comments about what we've just gone over. So I will move this screen and see if we can pull it up in 1 second. So cool. Data set being filled out in real time. And don't worry about formatting or anything. That'll be part of the learning process where we'll be able to correct some of the formatting. So it'll actually be better if we don't leave everything uniform. Oh, sorry. I was seeing everyone in chat. Yeah. We'll give it one more moment. And actually, if there's anyone who's actually going to be viewing this via recording rather than live, this link will still be active, so you can feel free to add that stuff in, and I'll check it and make sure that the data set, our course data set, will be updated next time. Almost there. Okay, all right, we're done. So I'm gonna download this. Oop, all right, give me 1 second. I'm gonna have to move that file over. So in the meantime, I'm hoping that everyone got the Canvas announcement to download and install R and RStudio. And so we're actually just going to go ahead and dive into the tutorial now. So I'm not, again, because of the way this is structured, I'm going to try my best to figure out how to get everyone to follow along at the same time as we're doing all this stuff. But if you need me to slow down at all, yeah, don't hesitate to let me know. Sorry for jumping around in the screen like this. I have to bring up some windows. Okay. So for those who haven't used R and RStudio, so as I was mentioning, R is a programming language put together by a bunch of statisticians. So the base package of R is sort of the back end, and actually RStudio is not actually an environment that I use, but I'll be sort of displaying it here because that's what I think I'd like folks to learn it in, and there are a lot of nice features about RStudio that make it a good environment to learn R. So RStudio is the interface is one interface program for R. And it features things like syntax highlighting, which is pretty nice. So if I were to say something like this, you'll notice the function is in blue, and so it'll separate things by certain types of colors. It has pretty nice functionality in terms of like right here we can see the auto close for parentheses. It'll tell you which parentheses you're on so that you can keep track of. So little things like that that make life just slightly easier for folks to learn. Okay, so this environment is the default for RStudio. You may actually have when you open it for the first time, this window here might not be here, and the way you get that is you just click this button here, which creates a new worksheet. Again, I realize it might be difficult to follow along if you're doing RStudio on your own. So again, just let me know if I need to go slower. So this worksheet here is kind of like a notepad. So you can type whatever notes that I want here, and that gets saved as whatever file that you're saving it in. And so if you're writing some kind of script or working on homework or project or your research, as you write things out in this area, everything is preserved. When I execute commands, say I want to look at what happens when I do 1 + 1. You can execute this command by clicking this button here, run, which will run the current line that you're in, or there's some keyboard shortcuts. If you're on a Mac, it's the Command Enter. If you're on a PC, it's Control Enter. And so if I go ahead and do that, what you'll see happen is down in the bottom in the console, it's going to run and execute that command. So you can think of the console as kind of like a, if anyone's ever used like a programming calculator, right? This is that space to do free operations. And so if I want to do the same thing, 1 + 1, I can type it down in the console, hit enter, and it'll just spit out the answer. But what you'll notice is that none of this stuff is stored. All of that is it's just it's just executing commands. Now you can actually go back to look at previous commands. So if I do 2 × 1, I can press the up arrow on your keyboard, and it'll look at the last thing. And if you press it again, it'll look at the thing before that. So that's a nice little shortcut to remember. So if you're repeating things many times, you don't have to keep typing it out over and over again. This area here is a viewer. And we'll look at this as it becomes relevant. You'll see that some things that we're doing here will give some kind of outputs that are relevant here. And actually, I bet some of you are probably more familiar with RStudio than me, so feel free to chime in if there's something that I'm doing in this interface that's dumb, and you can correct me. Up here is our global environment, and I'll talk a little bit more about what that means once we get to variables. So that's the basic layout. Let me pull up some notes here, and here I'm just going to go through some basic operations and commands. Again, you know, for some of you, this might be information that you already know or are pretty familiar with, but not because that class, Deb Niemeyer's old class, isn't offered anymore. I'm going to do a more sort of robust tutorial as we go through learning about R. Okay. So as I was showing, you can do some of these basic commands. So addition, you can do multiplication, and you can do exponentiation. So 1 + 2, and I can execute again each of these with the run command into the console. So if I execute this should be 3, this should be 6, and 3 to the 4th should be whatever 27 × 3 is. 81. Great. So pretty simple, pretty straightforward. So then there's a question of what happens if we want to store an object or a variable for use later. And you can use an assignment variable. So something like this. So X, and then you make this arrow thing, caret dash, which is R's notation for an arrow. So that will store this value, if I run it, as a variable. So you can see that it has executed down here. And so if I go down to the console and I just type X, then it's going to return whatever I stored it as, which is 2. And if I type any other variable, say I say Y, whoa, hang on a minute. That's weird. Okay, let's see. Apparently this is storing an old session. Sorry about that. Does anyone know how to remove all variables from the workspace. I only know how to do it one at a time. So, okay, so RM stands for remove. Oh, try clicking the little broom. Okay, here we go. Clear console, perfect, okay. I don't know if that actually just clears the stuff in here. Yeah, so everything's still stored. Okay, here we go. Thank you, Summer. Ah, yes, okay, I see what this is doing. Yeah, you're just removing all of them. Okay. Neat function. So if you click the broom, it clears everything from the space, but it's not actually doing anything to objects that are stored in the environment. So as you see, RM, which is what I did earlier, is a way that you can remove objects. So after I store an object, x is 2, I can type in ls, which will list out all the things that are stored. So you can see x is stored, and I can do rm to remove it. And if I do ls again, it won't be there. And if I type x after having removed it, then it's going to say error object x not found. Okay, so let's go back to storing the object. One thing that you'll see, which is pretty nice, this is not in the typical interface that I use, but you can see that objects get stored in this global environment space, so you can readily view a table. I'm going to actually quickly do this. So we'll learn more about how to do this loading data and such later on. So you don't actually need to do this, but I just want to demonstrate this is how I'm reading in CSV. So this is the course roster downloaded from Google Sheets that everyone just filled out. And if I run this, great, of course it doesn't work. 1 second. Ah, yes, it's probably because, yeah, okay, hang on. Again, this is because I don't use this environment. So part of it is anytime I want to load a file, again, which we're going to learn how to do later, you need to set your working directory. And the working directory is just pointing our software to your location in your file directory. And if you want to open a file, you have to point to the right direction. So usually you set the working directory to where the file is located. Again, apologies for this. I'm not used to this environment. So basically, I'm heading over to the directory in which I have this file saved and my course roster saved. And now I need to set my directory, which hopefully I can do somewhere. Nope. Did that do it if I just do it like that? No, it didn't. All right, we're going to do it manually. Okay, so now I should be pointing in the right place. And if I run this file, okay, this was all so that we could see what happens when I look at or load a data frame into R. So this is, I've loaded into this object, which I've called course roster, that data frame. And so you can see that here. So normally in the base platform, the way that I would view it is I would just type it in here. And you can see all of that data. One of the nice things about RStudio is that it has a viewer. Okay, actually I see a comment here about how to set it. Here it is. Okay, so you can click here and set as working directory instead of typing it out manually like I just did. Okay, so going back to here, for the data viewer, you can actually click here and it'll view it out as this nice little table, which is pretty nice. The version or the platform that I use and the base platform don't have this functionality where you can view it readily like in a Excel type of table with these cells. And so this is a nice sort of visual way of being able to look at this. Okay, so on this platform, just know that this part over here lets you look at stored objects. Okay, so I'm going to store another object, y, and now I can, as I was saying, I can view what these look like. X will be 2, y will be 3, and I can now perform operations using stored objects. So if I do x plus y, that's just going to be 5. I can also overwrite objects. Okay, so now that I've stored an object, in addition to removing it, I can just change its assignment. X is 3, and now if I do x plus y, it's not going to return 5, it should return 6, which is what we see. One question that always gets asked here is x equals 2. So if you're more familiar with working in other programming environments, this is more commonly the way of doing assignments. And it does actually work. X equals 2. And if I type x here, it will have reassigned it to a different value. And so you can use equals, but when in the R platform, generally it's considered better practice to use the arrow notation. And there's a really sort of nuanced reason for that, which I'm not going to get into. There is a really sort of edge case where the functionality will be different between the equals and the arrows, but you will, I almost guarantee you that you won't run into that. And in fact, I bet that of the folks in this course who are familiar with using R, then you've probably actually never run into that issue either. But I think there's a couple good reasons to use the arrow rather than the equal sign, even disregarding that super edge case. It's a way sort of distinguishing, it's a nice way of distinguishing the difference between assignment operators and equivalence operators. So you never get confused on that front. And so there is a difference between doing something like x equals 2 and x equals 2. And so the first one is an assignment operator, and the second one is checking for equivalency. So the first one says, assign x to be equal to 2. The second one says, is x equal to 2? And that's a common mistake of doing one or the other, and you can avoid that issue by doing having a separate sort of assignment operator in your head. So, you're welcome to use equal if that's what you're used to, but I think it's typically better practice to use the arrow. Any questions so far? All right, I'm gonna continue moving on, assuming your silence is complicit. There is a concatenate function, and so we're gonna start introducing built-in functions a little bit later on in the tutorial, but right away we're going to introduce one here because it's kind of unavoidable and it's pretty prevalent in everything that we're going to be doing. So C stands for concatenate. Yes, okay, I see a quick question here. If you want to take notes in the R file, what's the proper way to comment text? Yeah, so it's using a $sign. So if I want to make a comment, below is an example of the concatenate function. This is really useful for being able to take notes. So let's see. If I don't have this concatenate sign and I run this, it's just gonna break because it doesn't know how to handle all these symbols, which it thinks are sort of stored objects and not sort of words or notes. And so you can do that with this, and you can do as many lines as you want. Yeah. So actually, yeah, I was gonna quickly comment this. So C stands for concatenate. One other quick aside, actually, if I have a whole bunch of code that I want to comment out, which can be useful sometimes. Let's see. In my interface, there's a way to do this. If someone wants to pipe up in chat, how to do this in RStudio. Let me see if it works the same way. Nope, it does not. Let's see. You can comment. Okay, so it's Control-Shift-C. So let's see if that works. Yeah. So this can be handy, like if you have a batch of code that you want to comment out all at once, if you're doing like testing or something, you can comment and uncomment blocks of code using Command-Shift-C. So I'm going to just make a quick note of that for folks. Block. Blocks of commenting with cut command plus shift plus C. And I'm realizing that that's probably going to be different on a Windows machine. I assume it's going to be Control-Shift-C, but you'll be able to look at that. It's under the code menu right here, comment/uncomment lines. Okay. Moving on. Right, so let me show what happens when I run this. So this concatenate function, 1, 2, 3, 4, will give you a vector of numbers as opposed to just one number at a time. It's a pretty powerful tool that lets us create objects with multiple numbers or strings. I'll talk about strings in a little bit. Now let's observe some behavior with concat. concatenate functions. So, okay, so operations with vectors. So first I'm going to go ahead and store a couple vectors. So I'm going to have 1, 2, x2, I'm going to have also as 1, 2, and x3, I'm going to have 1, 2, 3, something like that. Okay. So here, let's take a look at some operations. So if I do x1 minus x2, you can imagine what this is going to look like. It's just going to subtract each entry of the vector. So this should return, oops, I didn't run these, 1 second. So here you can see that those vectors have showed up in the global environments area. And when I subtract x1 from x2, I get 0, 0. So 1 minus 1, 2 minus 2, great. Everything's working so far. Okay, Greg is asking, is this equivalent to a list in Python? Yes, kind of. There are some little differences with Python. One thing is that it's been a while since I remember all the nuances, but the indexes are different. Everything starts at 1 instead of 0 in R. And then the types that get the types of data that can get stored in different types of vectors and lists are going to be different from Python. And I'll show that. You'll be able to see, if you're familiar with Python, how that differs.
Also, Alan, just to pipe in on that, with lists, you can't manipulate those in Python. You can do that with NumPy arrays, though. So, like, I don't know how vectors work in R, but like with lists, you can't like scale them or whatever. But with arrays, you can. I think that's probably the more.
Yeah,
accurate.
array would be more analogous. That's right, exactly. Yeah, I think if you move from Python to R, I think the intuition will follow pretty quickly. You might get a little more confused if you went from R into Python, for some of those reasons that we just discussed. Expanding lists is done in a fairly sort of different way. Okay. Let's see, where was I? Okay, well, let's do x3 minus x2. So now this is going to get interesting. What you see happening here is actually you do get a returned value, x3 minus x2. So that's what is 1, 1, 2, 3 minus 1, 2. Okay, that's a little weird, right? So the first two, so 1 minus 1, 0, 2 minus 2 is 0. How the heck do we get 3 entries in the answer vector? So first of all, they will give an answer, but they'll give a warning message that the longer object length is not a multiple of the shorter object length, which makes sense, right? x3 and x2 don't overlap. So the behavior here can be a little counterintuitive. Essentially what's happening is it goes back to the beginning of x2, so it's 3 minus 1. And then that's how you're getting this 2 at the end. And so these are some types of things that you'll need to keep in mind and be aware of and watch out for as you do this, for some counterintuitive behavior when it comes to doing vector operations. So similar type of thing here. If I do x2 minus x3, same thing. It's just going to jump back to the beginning. I can do other types of operations, x1 times x2, and you'll get similar behavior, right? First element times first element, second element times second element. and so on and so forth. This one, again, x2 times x3, you have that same issue where the vectors are not multiple lengths of each other, and so you're going to get this warning message. You can do division as well. I can actually even multiply a vector by a scalar. And so as you probably imagine, if I do x3 times x4, it's going to multiply every entry in the vector by the scalar value. So it'll be 1 times 4, 2 times 4, and 3 times 4. There is a slightly different operation. Probably some of if you're more astute and into your linear algebra, and you hear me saying vector times vector, and you're seeing this answer like 1, 4, you might be a little bit confused, right? Because that's when we think about matrix multiplication, that's actually not the answer that you would be expecting. And so there is actually a way to do matrix multiplication, and that is like this. So if I have percent times percent, that's indicating that I want to take a different operator for matrix multiplication. And that's going to give your product as 5. Where I can't think of an example that we would actually do this in this class. I mean, if we were doing some of the derivations of solving for like coefficients in linear regression, this is actually useful, but we won't actually be doing that. But it's good to keep in mind if you are ever needing to do matrix multiplication, that's possible to do here. Okay, great. So actually, the other thing that you can do is transpose if you're doing a matrix. And so this will turn it, this will assume that it's a matrix. It's going to turn it in from a row vector into a column vector. And so when I run this, or sorry, a column vector into a row vector, it'll turn it into a matrix and transpose it. Okay. So that's some of the basics about doing operations and storing objects. The next part that we're going to cover is our functions. So a function, if we think about in sort of strictly mathematical terms, that's something like this, right? F of x or y is equal to f of x. And you might have something like x squared plus x plus 3, something like that, right? And so in this function, I can plug in a number and get out a value for y. And so that's really what a function is. It's same in principle. You have something that takes an input and gives you an output. And the very first function, okay, second function, because we already learned about concatenate. And actually, I guess we did transpose too. But one of the first functions that we're going to learn about is the help function. And that is going to, if you're ever confused about what a function does, you can use help to give you a primer on that. And so I can actually put in the first function that we did, which is C, and this should work. C, combine values into a vector list. And so it's going to open up in the help tab over here on the right-hand side a description of what the function does. And so here, it describes how you use it, C, and then you put in your input. And then there's some descriptions and details of how the function works, what it does. And then one of the useful things that I usually find is that it actually gives some examples at the bottom. So you can look through these in case you're, in case you're ever confused about any particular function. Actually, I wonder, yo dog, I heard you like using your help function, so we put a help function inside your help function. So this tells you what the help function does. Cool. All right, so as we go through these, if you want more documentation about a function, you can use help. LS, I had brought this up earlier. So this should give a list of objects that are currently stored in your workspace. So if I hit enter, you'll see course roster X, X1, X2, X3, and Y. This is going to be the same, I believe, should always be the same as the global environment being stored here. This is how we look at the objects stored on your workspace in the global environment if we didn't have this over here. Okay, what else? So we talked about RM. So RM will remove an object from the workspace. So I can do RM X, and that will remove X. This is something we've talked about as well. Okay, in addition to, well, okay, actually, I'm gonna skip that function for now. Some other things that we can do: mean, which will take the average of any set of numbers. So let's see, if I do the mean of, let's take our X3. Okay, actually, so one quick note to show you guys. So what's the mean of 1, 2, 3? If you're thinking the answer is 2, actually, you would be wrong. So here's where you need to be careful. So when I type in mean into the help function, notice that the object that you're passing as an input is a vector of numbers. And if you look carefully here, this is not a vector. These are just separate inputs into my function. And so really what I need to do is this, which will put in a single object vector 1, 2, 3. And now if I press enter, then it should give us the right value. So here, if I do X2, because it's already stored, or sorry, X3, it's already stored as a single object, I can do that and get the right answer. For X2, what's the mean of 1 and 2? You should get 1.5. Great. Okay. Another function that's going to be helpful, length. This is the same as len in Python. So length will give the number of entries in a vector or in a list, which we haven't talked about, but we'll get to. So if I look at X3, there are 3 entries, 1, 2, 3, so it should return 3. Similarly, if I do this for X2, it should give 2. And if I do this for length x, it is not going to work, right? Because we removed x. But if I put that back in, then it'll be length 1. Pretty straightforward so far. Similar to length, if I'm dealing with a matrix or a data frame, I can look at the number of rows with the function nrow. We have loaded in a table horse roster, and I can see how many lines that is with nrow. 26, and I can look at the number of columns that is with ncol, number of columns, 26 and 12. Max and min should be pretty intuitive. This will return the maximum value in a vector, similar with min. Take note again, this is going to be similar to mean, although in this case, the max actually is able to take in a set of objects so that the functionality is not quite the same. So if I type in help max, we should see that you can take in numeric or character arguments and not just a vector argument. There's a shortcut for C where instead of typing out all of the numbers like this, especially if I'm going out to like 1,000 or something, then you can see that this will actually be the same type of thing. And in fact, I'm just going to go ahead and go 1 to 100, right? And that would save me a whole lot of typing out down here. So let's store this object as z, so that we'll have that as a object to use for our next example. Okay, the next thing that I'm going to show is sample. Oh, this is actually another sort of nice feature of RStudio is a function autocomplete guide. So if you see here in this yellow bar, this will actually tell you what the inputs you need for the function are. So this function that I'm showing right now called sample is a way of basically drawing numbers from a hat. Okay, and so I'm going to randomly select numbers. And the set of numbers that I'm going to be selecting is the first input. And so I'm going to pick out of a hat the numbers 1 through 100. And let's say I do that 10 times. Well, let's say I do that 50 times. And I'm going to go ahead and run this. And it's going to pull numbers out of that hat. And it's going to randomly select 50 numbers. There is another option that you have in here called replace. And that's whether or not you're sampling with replacement. So as you pull a number out of the hat, should you put that number back before you do the next draw? So if I say replace equals true, and I run this, you'll see that I have a pretty high likelihood, let me just quickly scan, of repeating a number. Let's see. Well, okay. I'm not going to do this on the spot. But one easy way to do this, to see what happens is like if I sample 101 and I run this, what you can see is the default the default in the sample function is that it doesn't replace. So as I draw numbers out of the hat, if I tell it to draw more numbers than are in the hat, it's going to error out because it's going to get to the 101st draw and it's going to say there's no numbers left to pick out. So that's not going to work. But so this is the default, and this is the thing that errors out. But if I do replace the numbers, then as I sample, you're going to do 101 draws. And here I can absolutely guarantee that at least one number is repeated, probably more than one, because you're replacing the draws. Okay. Another handy function is called rep, which I believe stands for repeat. And here the inputs are the thing that you want to repeat. So let's say I want to repeat the number 1 10 times. Then rep is an easy way of doing that, as opposed to typing out C111111 like that. Rep can also actually repeat vectors. So I can do x1, which is the vector 1, 2, and I can do that 10 times. So then it'll repeat 1, 2, 1, 2, 1, 2, 10 times. And actually, the proper notation for the input of this function is times. So let's see. If I run that, it's times equals 10. And you can do a slightly modified version of this, where instead of repeating that vector 10 times, I can repeat each value 10 times. And this will give slightly different behavior. It'll go 1, 1, 1, 1 10 times, then 2, 2, 2, 2 10 times, right? And so you can actually see that for like a longer vector. So 1, 2, 3, 1, 2, 3, and then here 1, 1, 1 10 times, 2 10 times, and 3 10 times. And then you can even do both. Times equals 10, each equals 10. So here it's going to go 1 10 times, 2 10 times, 3 10 times, and each of those 10 times. Going back to the sample example, there are also, I'm not going to show this right now, but there are also functions called rnorm, runif, which are going to provide draws from a normal distribution and a uniform distribution, and you guys can look into what inputs you would need to make those work. I gave an example up here of Z where we want to do the sequence from 1 to 100. And part of that is like a direct shortcut to increment by 1, but actually you might want to do different types of sequences. So SEQ is the function for that. And the way this works is if I wanted to do the same thing from equals 1 to equals 100, that should give the same output as doing 1 colon 300. The power behind doing the sequence here is that you can actually increment it in a custom fashion. So I can actually say by 2, and it will skip, right, it will 1, 3, 5, 7, 9 instead of by 1. You can even do from 1 to 100 by increments of smaller than 1. So if I want to say by 0.5. then it's going to go all the way from 1 to 100 in increments of 0.5. Okay. So these functions are really helpful for a variety of things. And you can always, if there are common functions that you can't find, or that I haven't talked about, chances are that someone's sort of already made that already, and that's one of the big benefits of open source software. And we'll cover this in a bit, but you can actually install packages for customized functions, and we'll take a look at that down the line. Okay. Now the way that people build these packages is by making their own functions, and we can do that ourselves. Okay, and so here I'm going to show how to create your own function. So it's the same way as you would create any ordinary object. So I'm going to create an object called I'm the real mean. And it's going to, I'm going to assign it to this operator called function, which is a function that creates functions. Okay. And inside here, you put in your generic sort of input. So for the Python users, we indicate the sort of function environments. I don't know exactly what it's called, not with any spacing, but through these braces here. So everything contained within the braces is describing what's inside the function. And so so that the tabs actually, while they matter in Python, they don't matter in R. So I could have a couple tabs here, or I could have no tabs, but we'll be consistent because that's generally good practice. It's easier to read the function. So what I'm going to do here, okay, how do I take the mean of a number? Okay, I'm going to create a variable inside of the function called x, and I'm going to add up whatever it is that I put in my input. So that's this sum function. Sum will add up all the entries of a vector. And then I want to see how many entries there are in that vector, which we use with the length argument. And then we're going to say the output is going to be x divided by y, right? That's the average. It's the sum of all the numbers divided by the number of numbers there are. And then you return your output. Great. And so what I do here is I run this whole block of code, you highlight it, and then just run it. And now I have defined a function called I'm the real mean. Okay. And now I should be able to put in an object, a vector object, 1, 2, 3. Oops. And if I run this, it's going to return the average, right? And I can do that for my shorter vector as well, 1.5. Cool. And so now I've created my own custom function that does essentially the same thing as mean, although it's actually not quite as robust. Couple things to note here. you have this return function, which returns the output here. And usually you're going to need to provide a function, this return function, in order to get something out, but not always. You can have a function that has everything in a single line, and you don't actually even need to define any variables, and this will do the same thing. Even though I don't have a return. I will generally advise that you do have this because it never hurts to do it. It's never really going to slow you down. And it's generally good practice, right? I mean, this is shorter and more concise, yeah, but it has the potential to be harder to read. So we want to go with sort of best practices. Okay, so let's do, let's take a quick look at something. So if you have been astutely looking at what is contained inside of this function, you'll notice something interesting, right? So I actually have an assignment operator here, x is equal to. So when I do I'm the real mean, I'm just going to run this again. What it's doing is it says, okay, I'm going to take this vector 1, 2, 3, and I'm going to add it up. So x equals 1 plus 2 plus 3, which is 6. Okay, so x is now stored as 6. Okay, y is going to be the length of this input, which is 3. So y is 3. And then I'm going to do this operation and return the output. But if I look over here, and actually even if I type x here, x is 2, and it's being stored as 2. So that was our original value that we stored as the x object. But it's not actually changing to be 6. So what's going on here? When you make a function, you are operating in what's called a local environment. And everything that happens inside the function stays in the function. It's like Vegas, right? No information leaves except for what you say in the return. And so x here, you can actually there's a okay. I'm going to quickly say there's a function called print, which simply prints a message. Okay, so if I type that up here, it'll print this message, and that's a nice little way of troubleshooting within a function. You can print out statements, and so what happens here? If I run this function and then I run this, it's going to print out this intermediate step of x, and it tells me that x is equal to 6. Great. So that's essentially what's happening here, is that you're actually storing a local variable that doesn't propagate out into the global environment, and that's pretty handy. It doesn't pollute the namespace, which is sort of computer science lingo for basically talking about storing objects and variables. You may start to have lots of names and everything, and one way of doing functional programming is to avoid that by having variable assignment inside functions. And so just know that objects that are stored within the function don't propagate outwards. And okay, so I'm gonna quickly note that this has been asked before. So is it possible to actually have local variables be stored globally? And the answer is yes. And I'm going to show you how to do that. All you do is add an extra caret here. And that's an assignment operator that says assign to the global environment. And so now if I run this, you'll see that X has now changed to 6, right? It has passed the assignment from the local environment into the global environment. And you do that with this double caret. Okay. Now that I've shown you how to do that, I'm going to caveat and say that don't do that. That's really bad practice. There are lots of dangerous things that you could, well, I mean, dangerous relatively speaking, but you could have things stored in your global environment that gets overwritten because you've done this global assignment operator. And it can lead to weird functionality as well, especially if you have recursive things, iterative things that are happening inside the function. It can have really non-intuitive effects on your variable. And generally, it's just considered really bad practice. So don't do that unless you absolutely need to and can't figure out a different way of doing it. And I almost guarantee there's always a better way of doing that. Okay. Are there any questions, concerns, anything about the course or? Oh yeah, okay, so what is the difference? Okay, I see a question here. What's the difference between a global and local environment? So the global environment is everything sort of being stored across your default sort of workspace. And then the local environment are objects that are stored just inside of this function. Okay, and so that's what I was trying to explain here is that, your X's and Y's inside the function don't change when I run this input, even though there's an assignment operator. Yeah, and so the main difference is that you have different spaces that you're working in where you don't need to worry about writing a function with variable names that are going to get overwritten in the global environment or even stored. Like I'm going to change this to like ASDF and QWER. And if I run this, what happens is you're not going to, oh wait, this is going to break. What happens when I run this is like these, even though the function stores these locally, ASDF and QWER, it doesn't show up in your global environment. So that's some of the operational difference between global and local environments. As you work a little bit more with functions, I think it'll be a little bit more intuitive. Any other questions?
Yeah, I just have a quick question. So like during the course, as you're going through exercises and like they get more complicated and you're doing them in R, if people are doing them in like other programs, like trying to like translate it across programs, sometimes you're like poking around online and trying to figure out exactly how to do it in your own program. Do you think like in the past, has that, like how have students dealt with that? Do you think it's just better to just like, rather than trying to do it while you're doing it, just pay attention and then go back through like with the recording and like actually translate it to your own code?
Yeah. I think that's probably going to be the best way to do that. Yeah, I'm sort of all ears for suggestions about how to best follow along. I think it's going to be easiest for doing it in R for those to follow along directly, because you just need to switch between two windows. For those who want to do like Python, I guess what I would suggest is if you're doing it in Python, it probably means you're already fairly familiar with a programming environment. So it's probably going to be okay for you to be able to follow along without sort of typing out at the same time that I am. And so I would say if you're trying to do it in a different programming language, my suggestion would be to just follow along and then later go back and see how to translate that and do all the sort of lookups. Because yeah, things will get a little bit more complicated. You know, we're going to get to some functions that are, you know, pretty specific to R, and you might even have to like look up certain packages and stuff in Python, and that'll take time. So I would recommend doing that sort of not at the same time. I will say that I will be putting up all of the notes from this code up onto Canvas. You know, I'll save this, and actually I have a version of this that's of the stuff that I put up into the R worksheet that's going to be commented, and so you should be able to go back and reference that even without having to, you know, rewatch the whole lecture, which I know that I'm probably going to be going pretty slowly for some people, and also fast for other people. So, you know, we're trying to strike a balance here. So hopefully that makes sense. And yeah. I see a comment from Greg. For Python users, do we want to put together a Google Doc with translations between functions? Yeah, I think that makes a lot of sense, and definitely feel free to do that and share it with the class. Yeah, and you know, for those who are familiar with Python, and you're watching me sort of go through this tutorial, and you're going to be seeing me, you know, do some examples in class and whatnot. Actually, you'll actually find the syntax between Python and R is actually fairly similar, especially compared to a lot of other programming languages. And so I think that following along shouldn't be so difficult for the other users. Great. Well, I think that is going to be all I'm going to cover today. We're running up to our 2-hour session, so we'll let's end on a quick joke here. Can anyone tell me what is a pirate's favorite programming language?
R.
Aye, but his first love was always the sea. Okay, cool. All right, thanks for putting up with my corniness, and more seriously, thanks for putting up with having to do this online. Yeah, let me know if you have any questions or concerns, or if you have any feedback. That would be greatly appreciated. Until then, I'll see you guys on Thursday.
Thanks, Alan.
Thanks, Alan.
Bye, everyone.
Thanks, Alan.